So good morning, everyone. So let's get started with today's session. And okay, we'll continue with something similar what we have been doing for last little more than a week. Okay, and we'll take up. See, we have briefly discussed about resonance. I think most of you will have some idea what does resonance mean in case of LRC circuit. We'll try to again. We'll deal with this topic or this subtopic in a more specific manner. Let's try and understand what it means. This basically, let's say if we have a circuit which has AC circuit, which has RLC. AC circuit means this itself is not AC. We apply an EMF which is varying as a sine function. Source is this. We apply an AC source here, and this AC source we change only one parameter. We don't change resistance, we don't change inductor, we don't change capacitor. Even amplitude of voltage also is not changed. Assume that we have different sources. Keeping amplitude same, we can change the frequency of the source. And then you want to understand if we change only one parameter in the circuit, which is frequency, how would circuit respond? That's called frequency response. And this frequency response has a lot of application in a lot of practical application in case of communication. And actually the tuning of a radio, if you notice now we move the knob around. Earlier used to be kind of knob. The tuning process also depends on some of this behavior. So let's try and understand what is the effect of changing only one thing, which is frequency of source. And let's assume that we start, we talk of angular frequency rather than frequency, both are related to each other. Let's say we start from very low value of omega, and it's gradually keep increasing value of omega here, angular frequency, from a very low value without changing the amplitude of EMF. Only one parameter is changing. How would circuit respond? Let's say what is the initial starting point? Very low value of omega. So how would the total impedance, the response of the circuit, or we are talking more in terms of the current which will flow and power it will consume. And we understand here in case of circuit, power consumption depends on I. Higher is the value of I, higher will the power consumption. And later on we will understand also what significance power consumption has. To understand I, we need to understand value of impedance. So let's understand as we gradually increase omega, how would impedance change? R is not going to change, but XL will change and XC will change. This is a combination of value of L and the source. These two will change. So we understand when omega is very low, which of the value will be very high? At very low value of omega, yes, XC will be very high. And since XC is high, reactance will be high, hence impedance also will be high. So at very low value of omega, this value is very high. Hence overall reactance is very high, hence impedance is high, hence current will be low. And so that's we understand here. But as we keep increasing omega, what will happen? This term, as we keep increasing omega, XL. So initially, say if we write at very low omega, low value of omega, this will be something like this, which will dominate. XC will be greater. I could have written this something XC minus XL by whole square. But gradually, as you keep increasing omega, this term will decrease, this term will increase, as the gap also keep getting smaller and smaller. So what is happening? Let's uncap. Both reactances will change. XL will increase linearly, okay, from a very small value. Initial will be 0. If omega is close to 0, XL also 0. And initial value of XC is very high. It will decrease starting from a very large value. So can we plot a graph between omega, XL and XC? It's a pretty simple graph. This also a function of omega, which is omega into L into constant. This also is a function of omega, 1 by omega C. So it's possible to plot a graph between omega and XL and XC. And yes, hence we can also plot a graph between impedance also. How would the graph look like? So if we have omega on the x-axis and we have value of impedance as well as reactance on the y-axis. This is how XL will change as omega is changed linearly, and it's inversely proportional to omega. So it is like a rectangular hyperbola shape. So this is how XL will change, and this is how XC will change. But we are interested in actually what term is important is the difference between the two. We are interested in the difference between the two. So how would this value x, if I denote x as equal to xc minus xl, what will happen to this value x here? See, we understand here xl will keep increasing, xc will keep decreasing. What will happen to value of x here, which we call as a net reactance? The net reactance, the gap, what you notice, this is the something at any point. What is value of x here? This is a gap between the two. Xc minus xl mod. And what we notice here, the gap will keep getting smaller. And this point, what has happened to reactance here? What is the reactance at this particular point? When xc becomes xl, this point reactance becomes 0. And the point where reactance becomes 0, this value of impedance is maximum. Thereafter, so what will happen to value of impedance? Impedance initially it will decrease, reach a minimum value, and then again start increasing. So that's what will happen to impedance. As impedance start with very high value, comes to minimum value, and start increasing. So, so how the reactance changing? Reactance also will keep decreasing, reach a 0 value, and then start increasing. Impedance also, since the R value is not changing, it will also have similar. If I plot value of Z value, it will depend on R also. If it could be something like this. So Z value, the shape will be like this. It will reach a minimum value when XL becomes equal to XC. That's how shape will happen. This is something will be minimum when XL equal to minus XC. XL is equal to XC, sorry. And at this stage, power consumption will be maximum. So this is a condition of resonance, and so we use the term at this particular frequency, the circuit is in a state of resonance, and we can define resonance in 10 different ways. But I hope you understand what are the ways we can define resonance. What is happening at resonance? One way of saying, okay, resonance is when XL equal to XC. We can define resonance in terms of when the frequency omega naught, when XL is equal to XC, what value of omega this becomes equal? When omega naught is equal to 1 by root LC. Another way to define resonance is at resonance, impedance is equal to R. Applied voltage is equal to VR. VL is equal to VC. Power factor is 1. All are just coming from one relationship. XL is equal to XC. And this particular frequency, we call it as a resonance angular frequency. If we apply a source which has the angular frequency of the source is equal to natural frequency, what we call this term as omega naught, it doesn't depend on the source, it depends on the circuit elements, which is called a natural frequency of LRC circuit. And you notice here, for resonance to occur, both the things must be present. If circuit has only capacitor, no inductor, resonance phenomena cannot be observed. Or other way also, this has only inductor and no capacitor, resonance cannot be observed. Both must be present. And if both are present, it will have a natural frequency, which depends only on LC value. If applied source angular frequency is equal to natural frequency, then the resonance occurs. And at resonance, power consumption is maximum. And suppose this power consumption is being fed to something like a speaker. When the current is maximum, power consumption maximum, the sound also is loud. So you can understand that way also in power consumption maximum. If this current is being fed to a speaker where volume is proportional to current, when large current will indicate large sound. And when the current is small, power consumption is small, the sound also will be very feeble. And this phenomena is used something in amplifier kind of thing. We not to do, but we understand what is this. So frequency response of a circuit leads to understanding of concept of resonance. Resonance, this is a condition for resonance. Based on this, I can define several 8 different things of defining resonance. But once we understand, rest of things are pretty simple to arrive at. So it's nothing new. I think partly we have dealt with resonance already. So we'll go through some simple numericals. These are nothing new about it. We'll come to something like Q factor and all, which is also based on resonance. And then we'll also come into forced oscillation, which are also based on something like omega naught. So this is phenomena of resonance. And see, and when we draw this value of impedance, will impedance always lie above this curve? Need not necessarily. This value, what is the lowest value here? This value depends on R. If R value is small, Z also R is small, it can be like this also. But depending on the value of R, the minimum value of Z also will be equal to R. So if the resistance is small, it could be something like this. What does this curve indicate? This curve indicate at the state of resonance, it will have an XL is equal to XC. R value is greater than these two. When R is greater, the overall curve will be above this. When R is smaller than XL or XC value at resonance, the curve will be like this. But it will be minimum at what value? It is minimum at omega. Okay. And high value, it will approach. There will be small gap. This gap will be because of resistance. This will always be above LC curve, right? And we can also understand here what happens in what is this part of anything frequency less than omega naught. What is the nature of circuit? If frequency is less than natural frequency of resonance, the circuit will be capacitive. Why it is called capacitive here? Because for that frequency, for this is something, what does this part indicate? This part again, applied frequency is less than natural frequency of the circuit, or omega is less than omega naught. It is capacitive circuit. And other part, this is at the state of resonance. When frequency is greater than omega naught, it becomes an inductive circuit. That also pretty simple. I think it's easy to understand. So whenever XC is greater, in capacitive. When XL is greater, inductive. Okay. We can understand one way also. Suppose a circuit is given, and in the circuit, what we find, there is certain frequency. We apply certain source which has frequency omega, and at this frequency, what we notice here, XL is greater than XC. Okay, so what are the changes I can possibly make to achieve resonance? This right now, if XL is not equal to XC, it means the circuit is not in resonance. So what are the ways we can achieve resonance? What are the things I can change to achieve resonance? Just think of it. Assume that what are the parameters here? Suppose you have everything you can change. You can change one at a time, let's say. I can change R, or I can change L, I can change C. How do I change L? I can add one more inductor here in series. I can add inductor in parallel. I can add capacitor in parallel or series. I can change omega of the source. So what changes will help achieve resonance? How should our mind think? What need to happen to achieve resonance? Why it is not in resonance? If one of them is greater than other. Resonance both have to be equal. So what I need to do is pretty simple. So whenever circuit is not resonance, what changes can help achieve resonance? The quantity which is greater has to be lower, or quantity which is smaller has to be increased, either this or both the things together. So either decrease in XL or increase XC. How do I decrease XL? There are two ways. What is XL equal to? XL is equal to omega L. If I have to decrease XL, either I decrease omega or I decrease L. Similarly, I have to increase XC. How do I increase XC? XC is equal to 1 by omega C. If I have to increase XC, I have to decrease omega or decrease C. How do we do that? So either decrease omega or decrease L. How do I decrease L here? If inductor. So suppose I have one more inductor, should I connect in parallel or should I connect in series if I want to achieve resonance? See, since the aim is to decrease L, by adding in parallel, the effective L decreases. So if I add a suitable inductor in parallel, this could help in achieve resonance. Similar way to decrease C. So here also we have to decrease it. By decreasing C also we can achieve resonance. To decrease C, how do we decrease C? By adding a capacitor in series. Understand this part. Decrease C, how do we decrease? So capacitor value, if we add two things in series, capacitor decreases. Inductor decreases when we add in parallel. Property of parallel and series. So these are the ways we can do. For example, if XL is equal to 2XC, connect another inductor in parallel. We can connect another inductor in parallel. Okay, and connect other capacitor series. So these are simple questions. So all we need to, whenever circuit is not in resonance, we can achieve resonance by making these two equal. And you should understand this basic simple equation we can achieve. Let's look at some simple numericals, and I'll not spend much of time because this is something we have done similar questions yesterday as well. So suppose now we are specifically looking at resonance type of question. The circuit voltmeter reading will be 0 at resonance. So which voltmeter? There are several voltmeters connected. Which voltmeter will show a 0 reading? Which is easy to spot. I think all of you should be able to solve. Which resonance? Which will show 0 reading? We have done similar question. All of you, I think you think it over. If you're not clear, Just again rethink and understand what has to be done. This also is a common thing here. All of you notice in the fan also. You know what is the fan? Fan also has winding. I think most of you know. Fan has kind of several coils around. Those who have seen would have noticed. And moment we have several coils, it has an inductive property. And some of you would have heard also. How many of you know that fan has a capacitor as well? Has someone seen a small aluminum kind of this small cylinder kind of thing connected here? How many of you know that fan has a capacitor connected as well? Do some of you know? And then we'll discuss why there's a capacitor connected in a fan. Does anyone know the capacitor fan has a capacitor also connected?
Yes, sir.
Okay, now let's try and understand what happens. See, when we manufacture a fan by natural property, since it is winding, it will always have inductive property. I think that's easy to understand because it has winding. So let's say self-inductor and fan has a motor. It has a more electric phone. It has this much of inductance. Actually, this value seems to be too high. Actually, not be something. And we want to impart maximum power at 50 hertz. If power has to be maximum, what is necessary for power to be maximum? XL has to be equal to XC. So if the circuit has more of inductive property, by adding a suitable capacitor, adding a suitable XC, if they become equal, the power consumption in the fan is maximum, and the power consumption is maximum, the fan will run fastest. So let's not understand too much about the fan property, but we are the minimum what we need to understand. Yes, fan has inductive property, and because of inductor, if we want to maximize power consumption, I need to achieve a state of resonance. I have to add XL is equal to XC. What is the value of capacitance which need to be connected is fairly simple. From these two we can calculate. So what is the assumption we are making? It is implied that electric fan has a resistance as well. This is inductance and this has resistance also. And to achieve maximum power, rest all is simple understanding of AC circuit. Condition for maximum power by adding. So if the circuit is like this, initially the circuit we can visualize like this. So if there's a circuit, it has certain power consumption. And actually what is a little surprising, by keeping the source same, if I add one more element in series, which element we are adding in series? If we add one more element here, actually this element may have higher power consumption. This arrangement may have lower value of Z because they tend to cancel each other. So implied, so we can easily calculate. That's also, I think, this is a past question. Most of it should be able to calculate. Equate XL is equal to XC, and which is easy to calculate. Value of frequency is given. So omega is given. Omega is 100 pi. Let's look at this question and try to understand how we'd solve it. These are all part of this. I think expect all of you to solve yourself. They're pretty simple question. What all is given? LRC circuit. RLC circuit resonance can take place. Voltage across R is given. Resistance is given. Capacitor is given. What we need to calculate? We need to calculate VL here at resonance. Okay. What do we need to calculate VL? First of all, it is resonance. How do we solve this question? I'll just give a hint, and all of you can easily solve. So since it is a resonance, impedance is equal to R. So what is the impedance of the circuit? R itself is impedance of the circuit. Hence, I know the value of current also. And once I know the value of current, I can easily find out, since C is given, omega is given, I can find out XC, I can find out VC. And VC will be equal to VL, and I can find out VL easily. So that's a link. If you use this sequence, you can easily solve the question. Let's look at this question. All of you read this question, and this question I'll give you a couple of minutes. All of you think, how would you solve this question? See, this is first, let's say, get the information what is given in the question. There are two circuits. This one circuit contains resistance R1, L1, L1 and C1 is connected in series. It resonates at some frequency. Rather than frequency, let's write at omega naught. Similar ratio you can get for frequency also. So what will be the angular, what will be value of omega naught? That will equal to root of L1 C1. Or I can say omega naught square will be equal to 1 by root L1 C1. Basically, we can say what is L1 C1 is equal to 1 by omega naught square. I can write some constant k. Similarly, the second one also, if I write, since the angular frequency both resonate. Yes, Asha, you have any question or you have an answer?
Sir, sir, no, sir, I got it.
You got it? Okay. So this is, I'm just using the information given in the question. Second also is resonate at the same frequency. It means for the second one also, if I take L2C2, similar way I can arrive, this is the relationship given. L1C1 is equal to L2C2 equal to some constant. That's why then only they will have same, and it's very simple conclusion to come to. Both L1C1 is equal to L2C2 is equal to some constant which is equal to 1 by naught omega naught square. What happens if two are connected in series? What can you visualize the circuit if we connect them in series? What will happen? How many 6 elements will be there? Circuit might look something like this. If we connect all of them in series, this will be R1, R2, and similarly this will become L1, L2, and this will become C1, C2. Now, question is, what will be the value of frequency here? What will be the natural frequency? So here also what we need to do here, I need to find the effective value of L equivalent, and this also need to find C equivalent. And this frequency will be equal to 1 by L equivalent and C equivalent. Let's put those values. So that's what it is. So you can replace, and what we have to assume, some of you think, okay, is there a mutual induction? There's no reference of mutual induction. So we'll assume they are connected, they are wide apart from each other. So what will be the equivalent value of L? That's all we need to calculate here, omega naught dash. So what will be L equivalent here? If we know the property of inductor, when they are connected in series, equivalent value is L1 plus L2. And what is equivalent value of capacitance? 1 by C equivalent will be equal to 1 by C1 plus 1 by C2. We can write in number of ways, 1 by C1 by 1 by C2. And I put this value of C1 and C2 from here. C1 is equal to K by L1 and C2 by KL1. And we substitute very easily, you can find, we can easily solve. And we substitute, that's the only point. And I can just substitute here and you get an answer, pretty simple. Here onwards. So this will be L1 plus L2. So what is from the 1 by C1 will equal to L1 by K into 1 by you notice L1, L2 cancel out, and very simple. And this frequency also, answer is pretty simple. This frequency also is same as equal to, yeah, we can come equal to what value? We come into 1 by, this is also same as omega naught. The rest of this, I think, is simple calculation. All of you can easily figure it out. So that's what I think. The only thing we need to keep in mind is how it gets connected. And whenever more than one inductor and capacitor are connected in series, we can always replace them with the equivalent value. Okay, that's also a question I think all of us should be able to solve. What happens when, let's say in this case, a variable frequency is applied in RLC circuit at a frequency double the resonance frequency. Impedance is root 10 times the minimum impedance. What is the minimum impedance if it is LRC circuit? What is Z minimum equal to? What is the minimum impedance in case of resonance? Is equal to R, which is at what frequency? At some natural frequency where XL is equal to XC. Let's see the at resonance. This is what at resonance is. So the question is saying this is at the resonance, Z value will be equal to R, and that's what is given. Minimum and minimum impedance is R naught. So what happens at double the frequency? When the frequency double becomes double, F is doubled or omega is doubled. Which values will change? No, Z value will change. That's what we have to calculate. What it will be Z dash? It will depend on what will be XL dash be equal to. If XL is proportional to omega L, when frequencies become double, it becomes 2x, and XC will become equal to 1 by X. And we substitute, and this is equal to root 2 times what is Z dash equal to? We can substitute Z dash will be equal to R square plus 2x minus 1 by X whole square is equal to root 10 R. You can solve. You know, there's a one problem in the question. Does anyone notice they're asking the question asks what is the inductive reactance? This kind of questions, perhaps I think nobody can give a perfectly correct answer. Which inductive? See, there are two values of inductive reactance. One is inductive reactance value at resonance, and one is inductive resistance value. We have two values. One is XL, one is XL dash. This is at resonance. This is twice the resonance frequency. This wording is not clear which thing we are talking about, which inductive reactance. And whenever such thing is not given, we need to assume that is talking about one we get in a later state. So this answer is related to value of XL dash. We need to find the value of 2x. I hope, is it clear what I'm talking about here? Signesh.
Sir, I didn't understand how we took the capacitor reactance as 1 by x.
Sorry, 1 by 2x. I didn't write 2. Sorry. 1 by 2x. Okay, I didn't write properly. So this 1 by 2x. So this will become half, and this will become double. This also is an easy question. I think only thing you solve it. So this wordings are not clear. What does this wording apply? We'll assume what we can add this term. What is the inductive reactance when at double the frequency? At double the frequency. You solve for this. Okay, this question, let's see how do we go about solving this question here. All of you think, how do we go about solving this question? I'll just read through once and see how do we solve this question. It's a simple question. They're all substitution in mathematical equation. So here, what are things which are given? Source is given. Current amplitude at a frequency that is 10% lower has to be found. Okay, so 10% lower, if they have to find a current amplitude, voltage amplitude is given. To find current amplitude, what do we need to find current amplitude? We need to find the value of impedance. Impedance at what value? 10% lower than resonant frequency at 0.9 omega naught. So whatever value of XL and XC I have here, at resonance XL is equal to XC is equal to X. At we can easily find these values here. At 0.9 W, XL value XL dash will become equal to 0.9x, and XC dash will become equal to X divided by 0.9. We get those values and substitute, we can find an answer. So this also is something we can easily solve. These are all mathematical substitution. Using simple formula, you can get an answer. Okay, this also is a question. This is all part of your assignment today, and all this question you should be easily able to solve. Okay, I'm not going to go through. Let's come to another simple application. Same thing, we are talking about resonance, and there's a term called quality factor. And let's understand, before we understand quality factor, I'll take two examples. See, notice what is the difference in two cases, and if you understand the difference in two cases, you will understand quality factor a little better. So this is a circuit given here. This is RLC circuit. There's R value, L value, and C value, and it is connected to this source. And this example of, and at this particular, we can calculate value of XL and XC. At this frequency, if we calculate value of XL value also will come equal to omega is equal to 100. So XL and XC both come equal to 100 omega. So if we apply this source to this circuit, it's in the state of resonance. Okay. So this is in the state of resonance. And when in the state of resonance, the value of impedance will be equal to resistance itself, which is 10 ohms. Hence, current amplitude will be equal to 10. And we can calculate, and that's how the phasor diagram will look like. We have known that already. And we can calculate power consumption. Power consumption will equal to VI cos phi. Those are RMS values. They have to be RMS values. These values given here are peak value. I can calculate the power consumption when this source is connected to this circuit is equal to 500 watt. Okay, so this part we know already. I think most of it is pretty easy to calculate. What we are trying to understand, what happens if the source frequency is changed to something like this. So we are keeping the amplitude of EMF same. If we make the frequency half, what we are trying to understand, how would the power change and why would the power change? So would the power become smaller or lower, larger? Even before we do so, in this case, power consumption was 500. Will now power consumption now, will it be more than 500 or less than 500?
Less than 500.
Less than 500. Then what we have to understand, let's see how much is the reduction. Let's just get an idea of reduction. So what will happen when this becomes half? So if this was earlier 100, this becomes, if omega becomes half, this becomes 50, it becomes half, and XC, which was 100, becomes double, and hence reactance becomes 150. Earlier the reactance was 0, and we get some value of Z. I can just roughly, it will come to 150 square plus 10 square, more or less we can take it as 150. So that's value of, we can calculate value of I, and we can approximately calculate what we find here. When frequency is halved, power consumption, this current becomes 1 by 15 times, and power consumption becomes much lesser than peak value. By making the frequency half, source frequency half, everything else remains same. The power becomes more, it becomes less than a percent of our earlier power consumption. And this is simple numbers. Numbers are not important. I will do the same thing, slight change now. Slight change here. This was 10, and these are the values here. I am changing only one thing here. Let's look at this. What has been changed now? What is changing this and this? Only one thing has been changed. Earlier the resistance was low value resistance. Now change with the high value resistance. Now what will the change? We have to understand what is the change in power consumption, and power consumption has its own implication. Okay, this again example of resonance. So in this case, XL, XC. Now, sorry, so okay, this also no. Okay, this part I meant, this is 500. Okay, this I think I didn't change number. And in this case, initially itself power consumption is 10 watts. In this circuit, resistance become more. So impedance also become 500. Even minimum impedance also will be 500. Current becomes much smaller. Previous case, power consumption was 500. Now it is 10 watts. We are looking at, again, if we do something similar. What we have done here also, we have made the frequency half. When we make the frequency half, those two terms will change. R will not change. XL and XC, this will change. And again, we calculate value of impedance. And again, we calculate power consumption. What we notice here, the power consumption at resonance was 10 watts, and it drops to 9.2 watts here. So do we notice any difference in two cases? What is the difference we notice in two cases? Both the cases, we have dropped the frequency from resonance frequency to half resonance frequency. What is the difference we notice here? When you notice any difference between the two cases? First case low resistance, second case high resistance. What is the difference we notice here? Percentage change in power consumption here is small. Previous case, power became less than a percent. Here it is just dropping by about 8%. Here change in power is not so significant even when we change the frequency. Is this understood? So which case is the, basically suppose I use a term. What is sensitivity of power consumption to frequency of the source? Do you understand this term? If I use a word something like, what is sensitivity of power consumption to omega of source?
Delta B by delta omega.
So which case it is very sensitive? Previous case it was much more sensitive, and this case is much less sensitive. So are you noticing that one? So that is something, and that's a point which is captured in something called quality factor. And quality factor is a very small topic, and this is something just but sometimes means they also ask questions related to such tiny little topics. And quality factor is very simple, one simple thing. So if so you notice this curve here. So there are two circuits. One circuit, if we take two circuits, if L and C are same, only R are different. So one curve is in blue, one is in black. Which of the two curves you think the resistance is higher? That's the first question. The first case, which one is more sensitive? If I look at, is the blue curve more sensitive or black curve more sensitive? Where the change in current is more significant with the change in frequency?
Blue color.
Blue color. And if I have to ask you, let's say which of the two circuit, if LCR, if two circuit, which circuit will have higher resistance? Can you tell me? Two circuits are connected to same source, and this is a curve we have drawn for two different circuits, different LRC circuit. So which case the resistance is higher? Based on this curve, can we conclude which is having higher resistance?
Black.
Green.
The one which has lower current. See, at this particular point, see, this is the state of resonance. This is the state of, where is the state of resonance? This is state of resonance. At the state of resonance, here impedance is only equal to resistance. So current depends only on the resistance. It does not depend on, it doesn't depend on the reactance. So current at this point here is directly dependent only on the resistance. If current is half, it implies the resistance is twice as much. Can we conclude that part? Resistance in case of black curve is twice the resistance in the blue curve. Okay, so this is something the curve also you can look at the question. So I'll just come to quality factor, and many times I'll suggest that quality factor, knowing one formula is enough. Quality factor, if you want to understand it, it could be a little complicated topic, but normally not many questions are formed. This application is mostly in terms of tuning of radio and TV antenna. You all know this Mirchi radio, FM band. All of you must be listening to FM band. Who listens to FM band very often? Anybody? Any volunteer who likes FM band too much? And you know, it has certain frequency. This is something, yeah, this particular thing is 99.97.7 megahertz or something. What does that imply? See, this tuning also, let's understand what happens in case of the antenna. We have an antenna, and all TV stations, the signals are coming. And those signals are coming at different frequency, F1, F2, F3. And you will not understand too much, because you think that you can understand working of TV and radio. No, you cannot understand at this stage. We can understand some part of it. I'm trying to focus on some part of it. You all, I think this part is easy to understand. See, all the signals are traveling in here. All the signals are reaching. I'm talking about old system which used to work on antenna. Now it is a dish. Let's say this is antenna. Antenna receives all the signals. But with this antenna, it is connected to a source here. And this antenna, what we can do, in this antenna, we can change the value of LNC. Its natural frequency I can keep changing. When I tune, what I'm doing actually, when I'm doing tuning, I'm changing the frequency, natural frequency of the circuit connected to antenna. Ashay, what did I say? What are we doing when we are changing the frequency? When we are tuning a radio or when we are tuning a TV, what are we doing? What are we changing?
Natural frequency, sir.
Natural frequency. So if I set a natural frequency which matches with F1, what will happen? This current, this oscillation will get magnified and this will become very small. That is in case of force oscillation. So when we match the natural frequency to frequency of transmission for a radio station, that frequency signal only get amplified. It becomes like this. All others are small. You don't listen to that. So that's what tuning means. Tuning means we match the frequency, natural frequency of receiver set to transmitted frequency. When both of them matches, that gets amplified. Rest of them are become insignificant. They are like low frequency. The current is very low, insignificant. That gets amplified. That's the only thing we need to understand. It is making some common sense.
So the antenna is an inductor, sir.
And you see, an antenna is something which you see, don't understand too much, but this circuit will have an LC. The circuit which is connected to antenna will have an inductor as well as capacitor. Okay, we can change when we are tuning. What are we changing?
Frequency.
Frequency. So don't worry, by changing, we can when you are tuning, actually you're changing the inductor and capacitor value without knowing too much. I'm changing the natural frequency of the circuit which is connected to antenna. And when my natural frequency matches with incoming signal frequency, that frequency only gets magnified, and others are signals become small. You know, so if this is the source frequency, if my natural frequency is omega naught, which is equal to 1 million radian per second. If source frequency also 1 million per second, what will happen? It will match. But if I set my natural frequency, suppose by tuning, I lower my frequency. From where? What is the frequency here? Can you read this frequency here? What is omega naught here?
1.
1. Capital M indicate omega is equal to 10 to power 6 radian per second. So when, and if my signal also has what frequency? If my signal also has a frequency, same angular frequency at 10 to power 6, current will be like this. Now suppose I turn my knob. I turn this one, I change the frequency drops to something like 0.8 into 10 to power 6. What will happen in the circuit? Current will drop. From here to how much it has dropped? From here to the current has dropped to here. And the sound what we hear is proportional to square of the current power. What will happen to the sound also? I am here the sound of the song is pretty loud, very clearly I hear. Moment I shift the frequency from here to here, what will happen? You tried some of the old radio, slightly tunes out, what happens? Suddenly the volume drops. So that's how it operates. No more than that we don't understand. Now we'll come to more from examination perspective. What are the things we need to know about quality of circuit? Now, if there are two circuits here, one circuit somebody has a black color radio and someone has a blue color radio. So typically what you want when you set your frequency to incoming source frequency, it should be loud. But if my instrument frequency changes, I want it to drop suddenly or I want to drop it slowly. Which is a better setup? You can tell. If I change the frequency of my radio, do I want the signal strength to drop suddenly or do I want to drop it slowly? Which is better for tuning?
Slowly.
Actually, what will happen if you drop slowly? So even at a frequency, suppose this is 100 kilohertz. 100 kilohertz also hear the song. 95 kilohertz also hear the song. 90K also I keep hearing the song. In that case, what will happen if there's another channel? At which frequency? At 94, they will start overlapping. Are you following what is happening? Because there are multiple signals. So what we want, ideally what should happen, I should hear the song only in a very narrow band. Outside, it should not be heard. Otherwise, I'll end up hearing, have some of you noticed, sometimes we tune the radio, and if the tuning is not good, we'll hear the two songs together. And that's very irritating. Which one is better here? Sudden drop, higher sensitivity is better. That's better tuning. I'll come to that again. So let's see, so how do we define better tuning? How do we capture this part? So first of all, what is tuning? If resonant frequency is equal to frequency of signal received, that's perfect tuning. Okay. Then we define something else. What is sharpness of resonance? We define, okay, this is the maximum value of current. Sharpness of resonance we define in terms of, we define some term called delta W. So if I change from here, I change this frequency by what amount? Delta W. And this delta W is a specific value. Delta W is change in the frequency so that the current drops to 1 by root 2 times of maximum current, or power becomes half. Is this a statement understood? What is delta W for any circuit? Delta W is change in the frequency from the resonance frequency so that power becomes half. Since the power is proportional to our current square, the current should become 1 by root 2. So if this value is 1 divided by root 2, maybe something like this. And so this is Im by root 2. This is Im, blue color. This becomes Im by root 2. So what is my delta omega? This is my delta omega. Bhagyashree, are you following something?
Yes, sir.
You understood this point, what I said?
Yes, sir, I did.
Delta omega. Okay. So there's something super delta omega. So we defined what is delta omega. I'll come to there. I would only about, I think, 4 points we need to understand about quality factor, which from exam perspective. So I'll come to that one by first. Let's understand as much we can. Then we'll come to focus on what we need to remember. So this one I defined delta W. Delta W is change in frequency needed for current to drop to half. Power drops half, the loudness of sound I was hearing, it becomes half as loud. Okay. And this term, so if I can lower the frequency, I can increase the frequency. And so 2 delta W is called the bandwidth. That's a name used in communication. So what is the bandwidth? It is within the band equal. So within this band equal to if I use a frequency something like this, omega naught plus minus delta W. Within this, the power will be equal to or more than 50% of maximum power. That's of bandwidth. So the power or loudness or intensity of signal is at least 50%. That's called bandwidth. So what is the range of frequency so that power remains at least 50% of the peak power? Karthikeya, can you define what is a bandwidth? Range of frequency, range of angular frequency for which?
In which power becomes greater than
Or
or equal
remains
to
at least
50%.
50% of the maximum power. Does it make sense if we define delta? So this is how we define bandwidth. Why? This is a convention, the bandwidth. Now we define the term called quality factor. What is the quality factor? You notice quality factor is this, how the definition of quality factor is. I will not go into derivation, it's not necessary. The quality factor is defined as, it's a definition. Bandwidth also is a definition. Delta omega also definition, you can understand what does delta omega mean. So quality factor is a ratio which is a dimensionless quantity. What is omega naught here? Omega naught is the resonance frequency divided by 2 delta W bandwidth. Resonance frequency divided by bandwidth is a measure of sharpness of resonance. Higher the value is, more sharp the resonance is. Among the two curve, which curve is more sharp resonance? Is blue curve more sharp or black curve more sharp?
Fast.
If I go back to the previous example, I took one example where R was 10 ohms, another case was 500 ohm. In case of 500 ohm, the curve was something like this. You know, even with half the current, also the power didn't drop much. If something like this, what will happen? Bandwidth will become very large, which is not desirable. What should be there for? What should be required for? What you call? We can also sometimes use sharpness of tuning, and we can also use the term selectivity of tuning. So if somebody says, if what are the popular channels? Okay, Radio Mechi. If they say my bandwidth is 98.7 megahertz, it means I should hear sharply at 97.7. Ideally, it should be if I turn to 98.6, I should not hear the station. That's ideal. In that case, what will happen? I can assign 98.5 to some other radio operator. So this is, intensity should lie within a very narrow band, or what we are saying, the bandwidth should be very small. If bandwidth is small, the quality factor should be as high as possible. The higher, the better. Okay. And what is quality factor? If you calculate from here delta omega, quality factor is a dimensionless term. It comes equal to omega naught into L by R. The smaller the value R, better the quality factor is. So there are 4 points from exam perspective. One, of course, you should remember the formula. This quality factor is omega naught into L by R. If 2 circuits are given, can you calculate which circuit will have better tuning quality? The one which will have higher value of Q will have better tuning quality. So if 2 circuits are given to compare, we can calculate what is omega naught here. We can write in multiple forms. What is omega naught here? Root of LC. It can also be written in this form. So you can write in multiple forms, but you just remember one formula. And why it is easy to remember? This is dimensionless term. Omega naught has dimension of 1 by time, and L by R has a dimension of time. That's why it becomes dimensionless. L by R is nothing but time constant also. So omega naught L by R is my quality factor. Higher the quality factor, better is the selectivity. I should know how to apply the formula, calculate Q. Higher value of Q will indicate better quality of tuning. What is the bandwidth? Omega naught is bandwidth. And within the bandwidth, power is equal to or greater than 50% of maximum power. I think in all I mentioned 4 points, which you need to remember in quality factor. And if I look at last 2 years, only one question had come in mains from this topic, and this was the question. A question which had come in 18 offline paper. All of the circuit, this is an RLC circuit with voltage amplitude. Omega naught is 1 by root LC. The current exhibit resonance. What is the quality factor? They simply ask the formula. That was the answer. So some of the topics which people tend to skip or not pay much attention, mains also will find sometimes once in a while, every paper you will find one question which may come from a very tiny little topic which people tend to skip. If you go through your material also, you will not find any question on quality factor. But you should remember 4 points. What are 4 points I mentioned? You should know the formula of the quality factor, which is omega naught L by R. Other things we can arrive at. Second thing, you higher the quality factor, better the tuning is, or better the selectivity is, higher the better. If 2 circuits are given, compare which is better for tuning, the one with higher Q. Third thing, you should know what is the value Q stand for. Q stand for omega naught by 2 delta omega. And this is called bandwidth, that's third thing. And what is delta omega? Delta omega is change in frequency from resonance frequency, so that the current drops to 1 by root 2 times, power drops to half. 4 points we should remember about quality factor. Is that clear? Okay. So quality factor, that's enough. That's what you need to know. And the previous example, if you go through, I give previous 2 examples. What I gave was to help you understand. In one case, see, when L was 10, when omega was halved, the current became less than 1%. Whereas other case, the change was only 8%. When R was high, that's what this formula also indicates. If R is low resistance, quality factor is high, it means the drop is very steep. Sensitivity is high. And that's what the example also indicated. Okay. And there's another thing, a major part of it I think will start today. And this topic may go on till tomorrow also. It's related to damped oscillation. Damped oscillation we did in case first year. And first year also, I think we made an effort and we have not understood. Now again, we'll try not to understand damped oscillation. Hopefully try to understand this time. Damped oscillation. Let's try and understand damped oscillation in terms of spring mass system. And then we'll see how we can relate damped oscillation of a spring mass system to RLC circuit. Okay. So let's come to in case of spring mass system. So suppose there's a mass here and x is equal to 0. This position when spring is in natural length. X is equal to 0, spring is in natural length. What we understand when nothing happens, so see, suppose they have a marking here, and this point is here, it is minus 10 centimeters. So what we do here, we apply some force to the mass m here, this mass is m, when the spring constant k, and I press it by distance of 10 centimeter and release it. What we normally expect, if I release it at a distance, if I press it by 10 centimeter and release it, what I expect, and after pressing, I expect it to reach other side also, a point where x is equal to 10 centimeter. Plus 10 centimeter. This will happen only when there is no loss of energy from here to this point to this point. And that's what we ideally expect. It moves, keep oscillating between same amplitude. If I press it by 10 centimeter and release it, what I expect it to reach to equal distance on other side, and again back and forth, keep oscillating. Similar thing I can think in terms of pendulum also. If I have a pendulum, and if I swing the pendulum, in the pendulum also, if the oscillation is small, we can take linear dimension. From one side, from mean position, if I put a scale here, if this is 10 centimeter, and I release it from here, even before it reaches other point, I can expect it to reach other point. If this was minus 10 centimeter, I expect it to reach a distance of 10 centimeter. This is when there's no loss of energy. This is an ideal scenario. But when this thing, would it exactly reach 10 centimeter in case of pendulum? Will it reach 10 centimeter? No. It does not reach 10 centimeter. There is some small here, and gradually what will happen? Amplitude keeps on decreasing, energy keeps depleting. That's a damped oscillation. So second thing, what will happen? So let's try to understand here. So what happens? We started. So if we suppose what I check here, I release it from minus 10 centimeter, and it reaches a point which is only 9 centimeter. And so what has happened from here? 10 centimeter. Same thing I can take in case of AC oscillation. It has reached 9 centimeter. So at this point, I've had to say what is the amplitude here. We define amplitude as displacement from the mean position where force is 0. So when I released it, its amplitude was 10. When it reached here, what is the amplitude now? If somebody asks me what is the amplitude of oscillation, would I say 10 or would I say 9? It has, by the time it has come here, amplitude has dropped to 9 and it has become 90%. And if I continue, I think you can easily show that one also. And again from 9 it comes back here. Will it come to -9? Again, actually it will come to, if this has become 90%, again it become 90% of this, it will come to -8.1 centimeter. And likewise, it will keep on diminishing. That's what happens in case of damped oscillation. Second thing, let's try to understand. See, suppose it was ideal case. Ideal case, if I release it from -10 centimeter, it will go to +10 centimeter. But if I assume, if I take in account some kind of friction, there's air friction here. If because of air friction, now it is not reaching 10 centimeter, it has reached only 9 centimeter. Do you think it will take same time or it will take lesser time or it will take more time? Why it has taken, first of all, why it has reached only 9 centimeter? Because of air resistance, because of air present here, it was experiencing a force which is always opposite to velocity. Since the force is opposite to velocity, actually what has happened? Amplitude has diminished and time period has increased. That's the effect of dampening. What is the effect of dampening? Amplitude will keep on decreasing, energy will keep on decreasing, and time period will be larger than this. So when we observe, when we actually observe what will happen, when we actually observe, it may be something like this. So something will start from here, x is equal to 0. If I start from x is equal to -10, I find it doesn't come to x is equal to 10, it comes equal to x is equal to 9. So it goes from here to here. And then again it start coming back and it comes to something like 0.9 into 9 minus. It comes here not to the full distance. It keeps, its amplitude keeps decreasing by the same fraction. That's how it will keep oscillating. Again, it will become, when it comes here, it will become equal to 0.9 into 0.9 into 9. So it will amplitude. But what we observe here, whatever time it has taken to go from -10 to 9, if it has taken t1, t dash, from here also t dash, so even though amplitude keeps diminishing, its time period remains constant. That's a damped oscillation. So what happens in case of damped oscillation? What has what in terms of if you summarize what we understood in case of damped oscillation, what are things we can mention? Abhirup, what have you understood in case of damped oscillation? Which points have gone into your understanding? Damped oscillation, what happens? Compared to undamped oscillation,
The time period remains
diminishing.
constant.
Amplitude keeps diminishing.
Yes, sir.
Time period remains
Constant.
constant, but it is slightly more than undamped oscillation. And that's what we'll study tomorrow. So basically that's something we'll study in case of spring mass system. And then we'll extend the same logic in case of electrical circuit. That's a part of our study tomorrow. And the day after tomorrow is a small topic of transformer. Yes, Vignesh. So I'll stop here. I just gave a basic idea about damped oscillation. And we'll continue from this is something more in terms of example and intuitive understanding. And then we'll try to capture in terms of equation, and we'll try to understand what does the equation mean. Does the equation matches with what we are saying here? Yes. So it's in terms of so I'll stop here. But today's the teaching part, and we'll continue with this topic tomorrow. Damped oscillation. Okay. Yes, Vignesh, you have some questions?